review it in the future. This presentation is going to be the third part of the series that my colleagues Tim and Lindsay were talking about in our 3D Solution Spotlight series here. And we're going to talk about the manufacturing of this drone. Specifically, Lindsay in week 1 shows some of the nesting tools and how we can program those with the frame parts in there. My colleague Tim last week showed us how we did some of the molds for the outer shell mold. We're actually going to focus on a little bit more of that, and the other half of the mold, basically the core piece, this week, as well as doing using some of the mill-turn tools on the prop spinners there that you can see highlighted in green. So the first thing we're going to look at is how we're going to look at the manufacturing of the core piece. Tim looked at the cavity last week and showed us some nice little tricks here and there on doing that. But obviously with this piece, we've got quite a deep reach in here, so we're going to look at doing some 5-axis work in this. And I'd like to cover just a little bit about the different options in 5-axis to start with, and then we'll go start looking at the actual programming of it. So the 5-axis milling package, it's basically got multiple different cycles in it, so we can do multiple depth cuts. So if you're taking like a finish pass and patterning it, so you can kind of create like a roughing routine. We can do multiple depth cuts. There's also area roughing for things like impeller blades, where you need to actually use 5-axis to get to the actual the bottoms of an impeller blade, for instance. And also plunge roughing as well. So it operates similar like a drill cycle, often used on things like propellers where you've got a long reach because of the blades. No side loads basically with that, so because you're doing lots of little drill cycles to rough out the material. Module also comes with lots of 5-axis finishing cycles. Now what is different a little bit about CAMWorks as opposed to some of the other packages, they all come with the software. So if you're doing swath machining, if you're doing impeller machining, port machining, engraving, there's lots of different strategies available that are included in all seats of all 5-axis licenses that we sell. The other benefits are we can still use our database. The knowledge-based machining is a really core point of CAMWorks, and we can still use that same stuff that we use in 2.5-axis and 3-axis to save strategies to do this common stuff that we see a lot of the time. So we can reuse existing information that we've already programmed and already set up, maybe to help train colleagues, for instance. The other benefit of using 5-axis milling as opposed to, say, 3-axis is we can do full collision checking, not only of the holder, but also of the tool, the shank in the tool, and everything else. The other things we can do, even if you're just doing 3-axis, this multi-axis mill operation that I'm going to show you here allows you to actually program undercuts in 3-axis as well. So if you're doing anything with like keyway cutters or lollipop cutters and things like that, this also applies. Another thing that I'm going to touch on, which is quite nice, is the convert to 3-axis to 5-axis settings. So what that allows us to do is basically program a Z-level, a pan project, or a constant step over operation, something that you're used to in 3-axis, and take that and use the holder checking to actually turn it into a 5-axis toolpath. And that's a very neat and simple way to go and get started looking at 5-axis. It's also where a lot of people actually start working from. They'll get a 3-axis machine and they'll maybe go out and buy a trunnion, add the options in the control to go and do the extra couple of axes. And they're familiar with the 3-axis programming. You're familiar with, okay, here's a Z-level, here's a constant step over, here's a pan project. And then all you have to do is check a box and it instantly does all the gouge checks for you and converts it all over to 5-axis. So I'm going to show you a couple of the bits of that because it's really nice. And also, you can still do rest machining. So if you are using, if you want to use things like an STL file or the working process to calculate the toolpath from what's being machined so far, you can do that. So let's take a look at some of the 5-axis milling though, and we'll just bring up the mold part here, right here. So this is the core piece to the mold that we were working on last week. There's some pretty tricky areas in here, most notably the bit right here where the thickness of the plastic material is going to be made. So that's going to be the kind of most difficult part of this region here, but obviously we've got quite a deep reach down here as well to get to the bottom of this geometry. So we're going to invoke some of those convert to 3-axis toolpaths. But even just from a starting point, we need to start looking at kind of fixturing things. So a lot of times things like dovetail fixtures and dovetail vices are usually one of the ways that a lot of people fixture 5-axis parts just to get access to all different areas. Now, I'm going to show you a little bit about that later on, but the first thing we need to do is maybe do a little stock prep and go in and put in a dovetail. Now, the nice thing about being in SOLIDWORKS is I can save out a feature as a library feature part in SLD LFP, and it basically allows me to drag it on, drop it in here. It comes up with a little window, and then I can just locate where I want it to be, and it's going to automatically self-center it between those edges and then locate it at the bottom of the screen there. And it puts in my dovetail cuts to the standards that the manufacturers recommend. In this case, it was a 5th-axis fixture, so I had a 1/2 inch here and a 1/2 inch there, basically. So we've got our dovetail fixture cut into the model there, which is one of the nice ones. And those are usually just created through creating like a dummy template file, creating a feature in the model, going to the Save menu, clicking on the feature, and then basically telling it it's an LFP, a SLD LFP, a library feature part. And then just pointing it to a folder, and it just saves it right in there. So, and then just drag it in, drop it in, away you go, basically. So the first thing we probably want to do is just maybe face the back of the material over here and go in and cut those so we can actually mount it on our fixture. So I'm just going to switch over here, switch over to CAMWorks. We're going to put in a setup on this back side here. We'll go in and we're already in a mill machine here, so we'll just go and add a bit of material so we can kind of face it off here. So we're going to use just the bounding box one and say add an 1/8 inch either side, top and bottom. Oh, that's a wonderful start. My apologies for that. Looks like it thinks it's Friday, which it is. So let's just get that restarted here. Looks like it's trying to check out early. So let's just load up that one again here. We'll just drag and drop our dovetail cut in here again. Which is located on both sides and then the bottom as well. And then we'll go back over here and we'll just make sure. Now this was originally set. I've got a model here to show you some STL file options for cheating some of the simulations later on. So we're just going to set it back to this here. We'll give it a quick save. And then we'll go back in and start putting our setup on here. And we'll put in our face feature here as well. So we're just going to put in a face feature across the top. We'll let it calculate up to the stock here. We'll go and generate those and get the face mill done. Now, the other thing that I've done in here is I've been in and just created a strategy for a dovetail using the slot feature. So I'm just going to use a slot feature on this side and this side here. I'm not going to worry about the taper. I've got an allowance on this wall here, so the rougher is going to come in and basically avoid machining off that wall, and then the dovetail will come off and cut that anyway. So I've got a strategy saved, again, using the database as much as you possibly can to save yourself time there. So we've basically gone in there and just faced it off, cleaned it all up, got the dovetail cutter in here, and this was just one of the stock tools straight out the library here as well. So we got the fixturing set up. The next thing we're going to look at is obviously going to do some roughing on the top side here. So we'll go back, we'll put in our new setup here, flip it around to the top side, And then particularly when I'm doing molds where we've got different regions in here where we've got obviously a bulk material here that needs to be cleared out. But then we've got some finer details. So we've got a slightly smaller region here and an even smaller region here where we've got to go in and rough out as well. So I just actually going to create a strategy that allows me to do multiple roughs. So essentially what I just explained, a large rough, a rough with a large tool, a rough with a medium tool, and then a rough with a small tool to come back in here. So it's just 3 area clearance operations for the 3 axes. So even though we're talking about 5 axis, a lot of the roughing, if you can, is a lot easier if you're doing it in indexing in 3 axis. In this case, we don't really need to do much indexing. The reach allows us to get the tool down there to the bottom with some of the bigger tools. So in here, basically, we're just going to generate these, and I'll show you what the different paths that we're looking at in here are. So Tim mentioned last week about the volume mode toolpath. So in this case, what we're using is we're using a 3/4 inch tool. It's got an 1.5 inch length of cut, and we're using the volume mode toolpath here, and the depth of cut's basically trying to optimize the material usage here. So we're using as much of the fluid as possible, but it's then going to come back. So it's going to go down 1.5 inches, come back, and then work its way up the pod in 1/8 inch steps to finish off the material here. So I'll just show you quickly what that's like as the other toolpath is generating there. So you can see it's running as much of the fluid, and there's the 1/8 inch steps here that's going to come out and rough that material out the way there. So we get a bit of a bulk volume material removal, and then we're going to come back in and do some other work here. Now, you'll see here, in this case, I've got a 1/4 inch tool that's wanting to come back and basically work in there. So I'm going to just go in and set my rest machining, and I'm going to turn it on up here to the working process. So it's going to look at that 3/4 inch operation up here, and I can control what it exactly looks at in here, and I can control how accurately it uses it. So I'm going to use the fine option in here to get a nice fine toolpath in here. But what you often find with rest machining is it will pick up on all those little kind of cascaded waterfall type effects and try and put toolpath over there. So I'm going to show you what that's going to look like and make a suggestion to basically change it so it limits the areas where it calculates. So you can see this tool, this 1/4 inch tool, is trying to go back in and machine all those little cascades away, which is not what we want in this case. We just want it to sit around in the top. We could do if we wanted to, but I just want to focus it mainly in that top region. Now, there's a couple of different options. I'm using rest machining, but there's this over allowance option right here. Now, if we go back to that previous operation for a second, the depth of cut that we left behind was about 1/8 inch. So in this case, I'm just going to go ever so slightly smaller than that on this over allowance. I'm going to go -0.1 here. Now, this is basically going to allow it to calculate in less regions. So it was saying almost like an avoid or an allowance. Don't calculate where there's 0.1. So it actually restricts the material to generate in more of a focused area, so where there's more volume basically. And obviously that 1/8 inch here was all the way down here. We're basically limiting it. So try just using some of these options here. Try adjusting the over allowance, maybe somewhere closer to the previous step over amount, and that should maybe clean up some of your rest machining options. We don't need to calculate that toolpath since it's already been generated here. I'm just going to turn this off here and clear some of these and then get rid of this so we can see. Now obviously I don't want to go back in and do all of this with the 1/8 inch too. The other option is, rather than using the rest machining, is maybe going in and basically using some of the contain and avoid areas. So rather than operating it there, we'll just go in and right click and insert a contain area into this as well. So we can limit it by using either sketches or using some of the existing geometry. So in this case, we're just going to grab the option here, this profile, and we want to grab this other option here as well. But you'll notice the yellow preview doesn't show up. That's because we just need to set it over on the left here to multiple. We can also increase or decrease that area as well. So maybe we'll go, maybe, I don't know, 20 thou across, And then we can also control it to go 20 thou past the actual diameter, just in case the tool can't get in there, or we've got a little bit more material around that region as well. So we'll just let it regenerate. And that is another way of basically controlling where the toolpath generates. So you can either use the rest machining, you could go back and add in contain areas as well, and kind of play it by ear, so to speak. So now we're going to get on to doing some of the finished passes, and we're going to get on to looking at some of that convert to 3-axis or convert 3 to 5-axis toolpath. So we're going to just add a couple of operations in here. Obviously, I could have a strategy, but I want to kind of go through and look at some of the different options here and where you might use them. So the first thing we're going to do is look at, say, the Z-level. So the Z-level is a great toolpath for going in, doing kind of slices, vertical direction, basically. We'll go in and grab our tool, and going back to a point Tim made earlier, we're not kind of diving down into each operation and going and setting all the step overs and everything else, because that stuff takes time to generate and simulate. We're just kind of roughing out a plan in our heads and how we want to do this. So we're just going to go grab our tools here, and I've got a 1/4-inch tool, and it's got a pretty short reach here. But we're just going to grab that, and that's one of the benefits of using the convert to 5-axis and using the 5-axis is we can keep the tool short, so we keep tool deflection to a minimum. Even just a 20% extra in tool length results in 50% more deflection on your tools. So anytime we can just shorten that tool, we get less chatter, we get less impact. So obviously that is not going to get anywhere really past here somewhere if we went and generated that with 3-axis. So the way we kind of trigger these settings on to go and convert to 5-axis is super simple. Go to the Advanced tab, hit the Enable button. We can put a holder clearance here. So this is allowing the holder to get it within 100 thou of the part, and then it will convert it to 5-axis here. The other nice thing about some of this stuff in this region here is you can tell it to calculate a minimum tool protrusion. How long of a tool do I actually need to get to the bottom of a part? And it will actually calculate that for me and give me a value down here. So that's all I need for doing the convert to 5-axis, but I just want to put in a contain area to limit the toolpath just to go around this particular region here. So Z-level might be great for this one, might not be so good for this one. It all depends on how you kind of want to set it up here. But I'm just going to put in a contain area, and I've got a sketch down at the bottom here that we use. We could alternatively just go around and click all the edges as well. And we want to control it so this actually goes past this particular geometry. We'll go and let that generate. And whilst that's generating, the nice thing is I can keep working. So I don't have to sit here waiting for that thing to generate. But you'll see the first thing it's going to do is calculate a Z-level toolpath, slice it in the vertical directions. Then it will go back and convert it to the 5-axis. So we're also going to look at doing a constant step over whilst that one's generating. So we're going to go in, put a constant step over in here. We'll go and grab that same tool that we're using, that 1/4-inch here. Keep the tools nice and short. Now there's a couple of different ways this tool will work. There's contain and contain and avoid as the offset curves. Now if you put a contain in here, it's basically going to allow the pattern to offset from the contain area. So in this case, the contain is going to be the outside edge. Basically, if we set it to contain like this and go in and choose the contain area and use this bottom profile here as the contain area, it's just going to basically offset in from that. So it'll be like pocketing all the way in. But the problem is it's going to get a little confused in these regions here and start kind of switching back in the corners and doing all sorts of stuff. So the contain and avoid, what it does is it offsets from the contain and the avoid area. So it kind of blends. It's almost like a flow line, if you will, between the two. So I'm going to use that same contain area that I did for the Z-level. And you'll kind of get an idea of what I mean for this particular option as well. So we'll let the toolpath generate here. Obviously, it's not being set up to be the 5-axis yet, but you'll see what I mean by the contain and avoid. So This is currently doing the contain. You see it's just offsetting from the outside profile, and then it's coming in here and kind of getting confused what to do in these corners and kind of running pretty close to this wall. If I go and switch it over to contain and avoid, we'll also check on that holder for the convert to 5-axis as well. The toolpath will offset now from this inside edge outwards as well. So it kind of blends in. It will run around and create a nice kind of a few passes around the inside, a few passes around the outside, and then it'll just come back and clean out these corners here, which is a really nice option for this kind of geometry. The constant step over is actually might also work quite well for this top region. So we've got a constant step over here, and again, we're just kind of getting an idea on how we want to go and program this part here. Now, the other thing that we might want to do is use something like a pattern project down in here. Now, in this case, this is obviously a 3-axis one, and we're not talking about too much of a reach here as well, but we'll just do it for the sake of it here. We'll go in, grab our 1/4 inch again, and in this one, the flow line, again, similar to kind of the constant step over, but in this case, rather than using contain and avoid, we're using curve regions. And I've just got a couple of sketches in here just to save a little bit of time on grabbing these profiles here. So these are 2 curves, basically, that represent this edge here and the outside edge here. So it's going to basically kind of wander around this region in the top here. And we could check on the 5-axis as well, but since it's right at the top of the pot, we don't really need to kind of worry about that too much here. The last one that we would possibly use in this case as well is we've got some flat regions in here that we might need to go and clear up. So we're going to also put in a flat area to go and basically program those. Now, we've got a tiny little area in here, so I'm going to grab, say, an 1/8 inch end mill here. I'm just going to try and grab my tiny little 1/8 inch, not the ball nose here, this guy, I believe. Nope. There we go, that looks good. Now this one's just going to go in and clean up the flat areas as well. So we're kind of building a strategy, we're getting close. We'll just give it a quick save here. Now, one thing that I usually recommend is get this kind of flowing, get it close to where you want it to be, and then simulate. Now you can obviously simulate it at this kind of step over, take a look at what's going on here, and then kind of go back. Now, when you're working on some of the full 5-axis, you might be changing settings and trying things frequently. You might be going in and adjusting step overs, adjusting things to try and get a cleaner looking toolpath. Now, if you're constantly having to simulate all the way through things, that's not so fun. So you could either play with the full simulation up here, but the other thing that I like to do is, say for instance, I want to quickly get to the Z-level step over here. What I can do is if I hit Shift key on my keyboard and then click on the simulate button over here, it actually will allow me to do almost like a turbo mode in the simulation. It allows me to control quickly how it gets from the first few portions of the toolpath and get it to a point where I can see what's going on visually for the Z-level pattern. So it quickly simulates all the rest, gives me a relatively accurate simulation, but then I can just focus in on what the simulation is doing for the Z-level. So that's a really nice one, and it's just invoked using the Shift key before you hit the simulate button. So just hold down Shift, hit the simulate button, and away you go. And you can see immediately there, like the tool's actually tilting away and getting that holder out of the way so we can actually get around that part here. Now the other thing that I usually recommend is adjusting at this point, get your step overs dialed in, and then save out an STL file of the finished version. So what I've done, rather than waiting for that to go all the way through, I've just got one in here that I've saved out already before. So that's the one that you saw me kind of loading up before. I just saved one out of the finished version of all of those operations and everything kind of programmed. So now what it allows us to do is simulate just doing the multi-axis stuff down at the bottom, particularly when we're doing fine-tuning, lots of little generate toolpaths and stuff to try and get the toolpath nice and clean and accurate. But we're going to look at machining this this kind of flat area down here in the sharp corner in there. And having an idea on how you want to do it to start with is going to be the first point. Now, having an idea on how you want the tool to come in and approach this is going to determine on what faces and things that you select. If we have the tool coming straight down here, it might work quite well for this top region, but as it kind of twists and turns down this bottom region, you'll often find, particularly down here, the leading edge will bite into the surface or the trailing edge will bite into the surface, and it'll just look like you've hacked it apart. So we're going to actually tell the tool to come in the side and swath machine this all the way down and around here. So we're going to select these surfaces here, and we're going to go in and basically put a multi-surface feature in. And I'm going to use one of the default strategies here just to show you how we go and set this sort of stuff up. So we go and select some of the geometry here. You can also, if you use any of the color coordination in SOLIDWORKS to define colors for faces, there's actually some nice options in the settings up here for selecting all of these pretty quickly using colors. But we'll just insert that toolpath here. We'll just use a stock database one here, and then I'll go and tweak it to make it cut here. So in this case, we're not going to use a ball nose, obviously. We want a sharp corner, so we're going to go and grab, say, a 3/8 tool. Now the important thing in here is because we're going to be tilting it down the side, this distance across here is going to be important. So we need enough reach that the tool can actually get in past here. We could use the holder checking and the gouge checking to avoid this, but as soon as we start tilting the tool up, it might start digging into the surface here. So realistically, we need a fair bit of reach, and in this case, it's only about 2 inches for this particular tool here. So we need to make sure our tool protrusions be remotely close to what it has a chance at generating. The next step is to go and define, say, the pattern in this case. And then in here, we just want a finishing pass to basically come around here and clean this up. So I'm going to use offset from curve. Great for this type of thing, this type of geometry. The other option would be flow line between curves, but it involves basically selecting an extra set of edges in here. So, and again, I've just gone in and created a 3D sketch, so you don't just watch me sitting and clicking some edges in here. So we're going to use that to define the actual curve to follow, and that 3D sketch is really just that inside profile edge here. And we want to just generate one pass in this case. So we just want one pass. We could control the number of cuts down here using the limit section. We can obviously go in and set our entry retract. In this case, plain and Z works perfectly for us. But we're going to come across here and go to the kind of nitty-gritty. This is where all of your 5-axis controls are. And this is going a bit back to what I was talking about earlier about the different modules that some CAM systems sell separately. With CAMWorks, you've got access to these all out of the box. So if you're doing swath machining, which we're going to do, simple, type in a 90-degree here. There's dedicated tools for doing things like port machining. So if we're doing a port in here and we want it to come around and spiral down the surface here, this one allows it to basically tilt through a curve. So we define the curve through the center line of the port, and then we tell it to tilt from the start to the end of the curve and drive it that way. There's other ones, dedicated cycles for impellers and things like that for doing like similar to what convert to 3-axis. I use this one a lot for taking a 3-axis toolpath that I program in here and converting it to a 5-axis toolpath so it stays upright until it needs to tilt away, basically. But like I say, in this case, we're going to do a swath machining one. Really simple, side tilt angle, and the great thing about it is the images all help a lot. So the normal here is going to be the surface normal, which is normal perpendicular to that green surface. And we're just going to say go 90 degrees to that, which is going to go basically lay the tool on its side and machine with the side of the tool. So we'll go in, hit preview. Now we've got a couple of little areas in here where we've got this kind of skipping over here. Now what often happens is you're trying to associate geometry to an edge as close as possible. So if we're working very close to a particular edge, it might be hopping on and hopping off. So one of the great little tools that you'll come to love with this is this edge margin option here. This just allows you to generate a little bit further away. So now I could set this to say 2 thou and kind of increase it up to get clean. Now basically what it's doing is it's stepping away from this bottom edge in this direction here. So if we went something higher, that cleaned it up, but I just want to show you another option here. So if we just go crank it up to say something high, maybe like 8 thou, it's going to generate a little bit further away from the model. Now this is going back to a thing that I mentioned earlier. When we simulate, the reason I use the STL file is because we're making lots of little fine tunings and changes here. We need to make sure that we're not wasting time simulating all the roughing and all the 3-axis converted to 5-axis toolpath. We just want to see what the finishing pass is going to do, but I want to see what material is going to be left behind. So that's why I ran through it at a fine step over, saved an STL file, dump it in as the stock, and then we can just come back in here and we only have to wait milliseconds for it to load up basically as the stock here, but it allows me to come in and see exactly what this motion is going to do and see exactly what material is going to be left behind. And I don't have to sit there waiting for the area clearance and everything else to generate. So we're going to basically just look and see what the movement looks like in here. It's looking pretty good. Now it's due to the surface here, it's actually lifting off in the corners, which is great. We're not going to be rubbing down here. And it looks like it's coming in and doing a pretty neat job of clearing that geometry up in here. So there's a little bit of a ridge here, but one thing that you can see is right about here, there's a little lip, and that's that 8 thou that I was just messing around with. Now one thing we can do to kind of combat that is a little bit of a trick. We can actually use the gouge checking to tell it to basically adjust that. But the first step we have to do is force it to go deeper. So I'm going to go to the Finish tab, switch it to a negative depth along tool axis down here, and that's going to basically force it to cut into the model by 100 thou. So we're forcing it to gouge. But then by using the gouge checking in here, we're going to actually tell it to go in and basically retract it. So we'll just grab the gouge check geometry here. So it's going to go and gouge check all those surfaces, and then this is how we can control how the tool moves. So in this case, we're going to use a retract along tool axis. Obviously, the tool axis is horizontal in this case. So it's going to basically pull the tool out. So it's just going to be hitting that edge. So it means that we're running right down that edge. I don't have to massage numbers and kind of quickly generate things and test things out and make changes and so on and so forth. I just let the software do it what we paid it to do. So it's going to go in, gouge check that, pull the tool out to exactly where it needs to be. So you can kind of see it's right on that surface now, and you'll see a lot better finish come in because of that as well. So we're having less polishing to do. As Tim said, everyone hates getting polishing done. So we'll just let it load up the STL file again here, and I think I used about a 2 thou or maybe a 5 thou resolution on this, so it takes a little bit of time. But so now we can just go and simulate that and see what it looks like. Now obviously in here at the moment, we're just in a part file. We're not looking at anything like any fixtures or anything like that. We're not got any fixtures mounted. That's what we're going to look at next. So you can see here, if I just zoom in here, you'll see that ellipse just completely disappeared because we've got a nice sharp corner down here, which is perfect for what we want for doing this mold. So, and you can see when we compare the geometry here, we can see that actual, they come down the other side, but you can see the finish. And we've got a small amount of material here that we might need to polish out, but it's looking pretty good so far. So going back to what I was just mentioning here, what about fixturing? So I'm just going to give this a save here. We'll just let it do that. And I've got a model here where we're going to actually put it into an assembly. So I've got a fixture that I just downloaded from Fifth Axis Fixtures yesterday. So I've got a fixture. I've got a model of the trunnion as well here. You'll often find in some machines, and this is the model of a Haas UMC 750, so it's got the dynamic work offsets and the RTCP to control the tool positions and everything else. But in some machines, things like your VF series Haas and stuff like that, you need to know where the actual axes intersect to be able to program these. So by having it basically modeled in assembly, I know exactly that this is the interaction between the rotary or the tilt axis here and the rotary axis. It's right in the center here. So you need to know that the machine zero rotary position is called. So in this case, I've just put that coordinate system in here at that location. And then I don't need to sit here reprogramming the pod. I just saved all the material over on the other file there. I can just right-click on the pot in the part manager here and just import that toolpath that we just programmed, import it into this assembly, and now we can look at things like fixturing and everything else. So basically, we can just go over to the toolpath. We can maybe just let it do a light rebuild, make sure everything updates. It pulled in the different operations here for me. Now we can just let it generate the toolpath. And we can also go in and basically tell it that we have some fixtures in here as well. So in this case, we're just going to go and tell it, okay, we've got some fixtures as well. It's doing a little bit of generating here, so I might have to wait a second. But this is a great way of knowing where everything is. You don't want to be risking collisions just because you don't know where a fixture is, or you don't want to hit something basically, or you don't want it tilting to the wrong side and accidentally smacking something. So we just let it generate here. And when we're in an assembly mode, you go into the Setup tab over there on the left and hit the fixtures, and then you can just go in and select the fixtures that you want it to actually show in the simulation. You can actually also tell it to avoid it as well. So it'll actually wrap it around or feed over or wrap it over if you tell it to avoid them. I'm just going to let it basically do its stuff. Now the reason the face mill and the dovetail cut didn't come in is because obviously they're on the bottom side, and in this case we've not set our indexing up, so they're not coming in. If we did have other setups and stuff to face the side in here, if we set the indexing up here to 5-axis and set the rotary axis in the tilt, and then set the limits appropriately, this would basically pull in all those different setups for you as well. In this case, we're not going to do that because everything's mainly done from the top setup here. But basically, we can go in here. One thing didn't generate here, but let me just go back. I want to show you. We'll pull in that STL file again. Now, in this case, I'm just using a slightly different one with saved out of a different coordinate system because obviously we shifted the coordinate down to a different location. It needs that new reference point here. So this one's going to load up and basically put it right in situ here. And really the reason why I'm doing this is because I want to go in and point out a couple of things. When we're talking about multi-axis mill operations in an assembly like this, we've got controls over the entry retract. Now before we had it programmed and it was above here, that's because our coordinate system was above. Now our coordinate system or our reference position is down here. We need to actually factor that in. So we need to actually change that multi-axis mill operation to go further up here and generate above the pot. Otherwise, we'll be rapiding down through the fixtures. But the other thing is we want to make sure that the data that we're getting out of this and the program is actually set up correctly. Obviously, we've got the simulate toolpath in here, but this simulate toolpath doesn't show us the actual machine movements. It's showing us the tool moving around the pot in a certain way. So we can obviously see fixtures because we just added the fixtures in here. You'll see them pop up and show up on the screen here. But we don't have the machine movements. So you can see the fixtures just got loaded up. But we want to be able to see what the machine is doing and how the machine rotates. That's one of the most important things about 5-axis, making sure your actual machine rotates in the direction that you expect it to. So we're going to actually use machine simulation in here. Now the machine simulation in this case triggered through this drop-down menu at the bottom here. I've got a UMC 750 machine in here. We're going to go and select the post as well, and we'll just need to hit generate. So I'm just going to simulate this last one anyway, so I'm just going to show you and generate that last toolpath. But what the machine simulation is going to allow us to do is basically post G-code. So unlike a lot of other simulators where we're using the CL, the cutter location data, which isn't the actual true G-code, we're actually using the posted code. So the first thing it does is it launches my window, so I actually post the code. Now I'm just going to run through this code here, open it up, and it's going to launch the machine simulation tool. And whilst it's just loading up that pictures and the images of the STL, it should only take a second here. I'm just going to kind of go back to a little bit around why we use machine simulation. Basically, some of the benefits are we can use it as an offline verification of the G-code. We don't have to stick the code in the machine and check and tie up a machine that cost us hundreds of thousands of dollars and tie it up just testing code out. We can test that offline, keep the machine running with programs we know are good. It also supports 5-axis mills. It does B-axis lathes. So if you've got the 5-axis Mazax and things like that, the B-axis Integrexes and things like that, it'll do dual turrets as well. So you get complicated machines nowadays. You've got dual turrets to worry about, main spindles, sub-spindles. You've got transfers and everything else between the two. This virtual machine software will actually simulate all of those. So there's no need to tie up that expensive equipment, just proving out or testing out code. You can keep the machine running on code that you know is good. You can also make edits to the code. So you can actually edit the code in the software and see what the changes do on the screen. So if you're, I don't know, making changes to, say, a Z move to make it go to a different position or something like that, something that you would normally see on the actual machine, you can see that in here as well. It will show you full collision detection on the machine. So if the tilt axis goes out of bounds or the head decides to ram into the main spindle for some programming error or a post issue, for instance, you'll catch those before you see them on the machine. The other great thing about this virtual machine, it comes in a few different flavors, but the premium version allows you to post from any source. So that could be another CAM product. It could be a standalone post tool. Anything that you can create a G-code text file, you can actually input that into the premium version. There's a lot of companies these days that be struggling to find different employees with certain skills. So it's hard to find programmers for a particular software in these cases. So a lot of the times companies will end up with maybe one guy running one software, another guy running CAMWorks, and another guy running a different software. Well, you can plug them all into the premium version of the virtual machine and basically prove out the code that way. So we can just bring up the code right here. It's loaded up the fixture, it's loaded up the STL file that I used as a stock here. And then we can basically play through it here. And if there's any issues in here, if there's any errors, things like that, if there was a tool change going to a weird position, if there was a gouge or anything like that, if we have any nozzles hidden anywhere, we can see all of that. We get a message window at the bottom of the screen, and we can see what the result is and if there's any collisions and things like that. If there's any axis overbounds, you can also do things like control the view layouts and things like that, so I can look at the part in one view over here on the left, see what the actual part looks like, and then I could be looking at the machine whilst it's running as well. So, and like I say, if you make edits to this, if I say, okay, in this line I want to make it go to, say, Z12, when we play through it, you'll see I think it just flicked it up there just ever so slightly when I first went through that. So it just kind of did a zigzag up at the top here. there. That's the Z12 move that I've just basically added in there. So you can see those movements and actually edit the code as if you're editing the real code that you run on the machine. So that's where machine simulation really comes into play. The next thing we're going to look at is doing some live tooling lathe work. So we're going to look at machining the spinner for the prop, basically. We've got this little drone. We've got these blades that fold in, and we've got this spinner on the front here. Now we're going to do this on a twin spindle y-axis type lathe. So we've got basically single turret. We're not worried about the two tools and things like that, but we're going to do main spindle, sub spindle, how you program those, and do all the milling as well, and how you can control different areas of the tool path and things like that. So, but just to kind of talk a bit about what the mill-turn package allows you to do, we can do programming up to 8 axis, so that includes the C-axis lathes, the C and the Y-axis lathes, and the B-axis, as well as the dual turrets where you've got the tool at the bottom and the tool at the top, or the front and the back, however you want to refer to it. It'll still use the feature recognition that you find in 2.5 axis and 2-axis lathe. It will find the face features, OD features, ID features, grooves, pockets, holes, all that sort of stuff in slots. For any kind of 3-axis surfacing work or any wrap features or any 5-axis simultaneous, you program it like you would do normally on the milling side. You insert the feature surfaces, and then you basically tell it, okay, here's the strategy that I want to go and use the database to generate. So you can still use the knowledge-based machining throughout this. You can quickly switch between a y-axis and a simulated linear move using the XC moves with just a click of a button. And you can do all the programming for sub-spindle transfers and handoffs right in the software. If you do have the twin turret machine, there's also a tool called the Sync Manager, which allows you to synchronize the two turrets, so you can actually have the two tools cutting at the same time and optimize the cycle times by synchronizing the two tools to cut at the same time, basically. So let's take a look at that. And we've got the spinner right here. So we're just going to go over here. We're going to go and set in the machine. Now I'm going to use a coordinate system in this case. I've got a coordinate system on the front side here. So I'm going to do the chuck, the hexagon and the grooves and the front half of it on the main spindle. And then I'm going to transfer it over to the sub spindle and basically turn the spinner cone here and drill the holes on the back side as well. Now, we've got to basically make sure the chuck clamps down on this. Obviously, it's quite a small little thing, so we're going to basically clamp it as well as we can. But we're going to basically set the coordinate system up there. We'll go in and define the stock. We're going to add, say, just 100 thou to our stock here on all sides. And then we're going to use the feature recognition. Now, the best way to approach it when you're doing this type of stuff is to get a plan before you start going and using the generate operation plan. Figure out how you want to go and cut that particular part. So in this case, we've got a face feature that comes in on the front here, cleans it up. We've got an OD feature, but it goes and finds all of this profile. Now, we don't want to do it that way. We want to do it so that we basically do the front half on one side and then back half on the sub spindle. So I'm just going to hold down the control key, drag the OD feature here, and then I'm going to make some changes. So the first one is we're going to do this on the main spindle. So I'm just going to delete that profile here, edit the actual profile to be just this portion here for that. And then the second portion, we just get rid of that profile, and we're going to go from here to here. And this is how we deal with the sub spindle. So this is where we're changing it to basically generate that particular profile on the sub spindle. And we're going to still do the rough and finish. So the groove is going to be fine. It defaults to the main spindle when you're going to do these. So this will be fine for the main spindle. Now this is actually a threaded hole to thread straight onto the motor. So we're just going to change that over to my thread cycle here. we're going to go use the tap instead of the thread and the boring bars. So we're just going to use a, say, a 1024. Quick rotate for that. Now there's some other stuff that I found in here that it wants to go and cut. Now I don't want that, so I'm just going to delete this one out of the way here. So we'll just get rid of that particular profile. Now in this case, this particular setup is really geared for the, so you see the direction down here. This is coming from this particular direction. So this drill will actually do on the sub-spindle. So we'll switch that over to the sub-spindle. But we've got the threaded holes in the same direction. Maybe we want to do the threaded holes because we don't want to run too close to the chuck on the sub. We'll do those on the main spindle. So this is actually from the opposite direction down here, coming in this way. So we'll do the holes for the threads on this side, and then we'll do the holes for the opposite side for the through holes on the sub-spindle here. So we just need to make sure that's set to the sub, and then this should be set to the main spindle, which it is. Now, when we're looking at this, the feature recognition found these as an irregular slot. Now, if you've got a C-axis machine, you could probably just index this and run an X move to go and cut this. We're going to assume that we've got a Y-axis machine. So we're basically going to go and just delete these profiles out and just kind of add our own in to how we want to cut this profile and the hexagon here. So we want to cut them from this particular direction. We're going to go and define the 2.5 axis feature. And the first one I'm going to do is just a boss. I just want something to run around the hex. In this case, I've just got a quick sketch to go and define that profile. And we want to go and run it up to just that flat there. And this will be done on the main spindle. So it's just going to generate a single pass with a 1/2 inch tool, as you can see over here, to go and cut that particular profile. The other thing we want to do is add an open pocket in this case to go and machine kind of the tri-Y shape here. So we're going to use an open pocket to go and grab that profile. And we're going to set the depth up to this particular position. And again, this one's going to be a rough and finish, and on the main spindle, this one. So now that we've got a plan in our heads on how we want to go cut this, now we can start looking at generate operation plan. The key thing here is when we hit generate operation plan, it's going to go and generate the appropriate sub-spindle setups for us and main spindle setups for us. So these are our main spindle setups here. You can tell because the two at the bottom here have the sub at the end of it down at the bottom here. So that's how we differentiate between main and sub. We can generate the toolpath and see what we've got. Now everything generated. The first thing we probably want to do is go in and set up all the things like all the program zeros and everything else. So origin point, we're on the front edge here, so that shouldn't be an issue. We're going to set this up to G54, and I'm going to pull my chuck back a little bit away from this. So we're just going to move it away so we've got enough room to come in here and groove this particular profile. So that's our turn setup. We'll do our mill setup here as well. So our origin wants to be the same as the turn operation setup as well. Again, it's going to be G54. The chuck location should be in the same location. But for the subs, we're going to set these up as well. So we just need to go in and say, okay, in this case, it's going to be the other end of the pot, and we're going to have maybe our z-axis is in the opposite direction on this side. And maybe we're going to use a G55 for this particular location here. But we need to define where the chuck actually sits in this case. So you check the box, and we want it to come onto this flat over here. So I can just click on the flat, and it defines that location, and then I can bring this flat over here. Now we just need to adjust where this actually clamps down. I think around 1 inch is, it's getting pretty tight on here, but that should be about okay. So by doing this, before we start looking at any simulations, it's going to ask us to do the updates. We'll also just do the mill pot setup as well. We're going to set that to 55 since this is going to be done on the sub spindle as well. We'll use the turn setup 2, and we'll just let it all regenerate in here. So now we can start looking at simulating it. So we can see what our toolpath is doing. I often like running operation by operation in this case. So you can see, you can kind of slow it down so you get an idea. So that's the facing operations coming in here. It's now doing the OD rough, OD profile, coming and doing the groover, center drilling the hole in the middle, doing a little pecking into the hole, and then coming and tapping it. And now it's doing the pilot holes for the threads in those small holes, coming in and doing the threads in those as well. And now we're doing the hex as well in here. So you can see the hex movement. In this case, it depends on what your machine is capable of. I'll show you where you can change those and how to deal with that sort of stuff. We're also doing our profiling of the outside there into the kind of Y shape. Doing the finish pass around those. Now the subspindle's got it, and now we're doing the OD profile. But there was nothing in there to transfer it over to the subspindle. So currently, it's as if I manually programmed it and then pulled the part out and chucked it in the subspindle manually. So I'll show you how we go about defining those. So there's the toolpath, but we need to tell it basically it's now going from the main spindle to the subspindle. So we need to actually put in the transfer. So in this case, we're going to put it in this mill pot setup. Since this is the last operation on the main spindle, I just right-click here. We'd use new subspindle operation, and this is where we can create templates for frequently used strategies for subspindle transfers and control over the subspindle. So one of the situations might be maybe we wanted to come over with the subspindle, grab the pot, pull it a certain distance, and then do a cutoff or a face feature just to face the backside of it. In that situation, we would probably do something like grab and pull by distance. So the subspindle comes over, grabs it, pulls it, we do an operation, and then we put in another subspindle up maybe to take it to subspindle home position. In this case, we just want a standard transfer, take it from the main spindle, put it in the subspindle. So we're going to go with a standard transfer template. But in this case, if you click through the steps here, we want the subspindle to orientate correctly to the jaws and onto the hex here. So we need to put in a 30-degree angle for the sub. So it now is coming over. The Z is the rapid Z, so we're just going to basically tell it to wrap it over to somewhere approximately around here. And then we want it to basically be somewhere around, say there, so maybe 0.95 or something like that. Maybe a little bit 0.92. Then we need to clamp down, and you'll see the actual images as you step through. The pressure builds up with a dwell cycle. The main unclamps, lets the pressure off, and then takes it to subspindle home. So that's kind of how we deal with some of the transfer side of things. And that's really, actually one more point was I was going to talk to you about how you control the operations for things like Y-axis versus XC moves. So on the NC tab of the operation, it's all to do with this rotary axis mode down at the bottom here. This relates to the C-axis. So is the C-axis free, as in it's rotating, or is the C-axis fixed? i.e., are we doing just a linear move in X or Y? So if we're doing fixed, it will output the Y moves. If you're just got a C-axis machine, typically on this type of geometry, you'll be using free. So, and you can also tell it to output the polar and cylindrical coordinates here as well. And with that, that's the end of the presentation here. If you missed any of this series of webinars, go check them out on the Hawkridge website. There's a tutorial section on the top. Hit the CAMWorks, and they'll all be posted through there. But anything else, thank you very much for attending, and we hope to see you next time. We'll be hanging around, actually, for questions. I see there's a couple of questions coming already, so if you see the questions page, feel free to just send a question. We'll be hanging around for a little bit just to get your questions answered here. So